So now, your empirical rule. The chart I gave you is divided into halves. But the one from the book is the plus or minus 1, plus or minus 2, plus or minus 3. And your rule is plus or minus 1 standard deviation is 68% of your data. Think of making a mountain out of sand. Most of that sand goes in the middle. That's where most of your data sits. Plus or minus 2 standard deviation as it goes out is 95% of your data. And plus or minus 3 standard deviation is about 99.7% of your data. You still got a little bit of pieces on the end. And when we look at this again, we're going to see that those ends come out and never stop. They kind of like are an asymptote, like when your line rides alongside of it, never touches it. So if you do this, easiest way to do this is to set this up on your graph. Put the mean in the middle. M, mean, median, mode, middle. Go out 3 standard deviations up, add your 4 each way. Subtract your 4. These are your numbers that correspond to 1 standard deviation above the mean, 2 standard deviations above the mean. And you can absolutely start like this. 67 plus 4. This will give you 71, 1 standard deviation. 71 plus 4. This will give you 2 standard deviations above the mean. You can do it the other way, 67 minus 4. 1 standard deviation below the mean. You can do it that way if you want, but somehow you should, I think the chart is helpful, and actually when we do this, most of the time we do this, we're going to use this sketch, because this is a good way for you to see where your negatives and your positives are. These are standard deviation scores that you're going to find on the bottom, and right now you can only find the whole numbers and the half at most. Pretty soon you'll find all numbers in here. So find your distance now between your 67, 63, and your 71, plus or minus 1 is 68%. If I said between 59 and 75, what would you say? 95%. Good. If I said less than 67, what would you say? $50. You're right in the middle of your chart. And what do these all add up to? 100. So what is half of 100? 50. So half of it's below the mean, half of it's above the mean. Doesn't that make sense for your average? Yeah, your middle, think of your median. Isn't the median the middle of your data? Half of it should be below, half of it should be above. Okay, 30. Same situation, you want, but they asked it the opposite way. They gave you the mean, they gave you the standard deviation, and they said between what 2 values does 95% lie? That's your plus or minus 2. On the chart I gave you, you have more detailed percentage. So if you went to plus or minus 2, and you started with your 70, add your 8, subtract your 8, subtract your 8. If you went from here to here, you could actually just add those percentages up off your chart. They're a little bit higher than 95 because it's got a decimal in there. Like we do 68, it's 68.2 technically. So it's a little tiny bit higher. But your empirical rule is just rounding. And number 31 says go back to example 29, this guy, and assume the number of vehicles in your sample is 75. This is what a lot of you forget. This is how many you're testing. Estimate, out of those 75, how many vehicles would be between 63 and 71 miles an hour? You told me 68% of the vehicles would be between 63 and 71. So if 75 vehicles come through, 68% of that 75 should be between 63 and 71. So 68 times 0.75. Right underneath it is just another sample size, a sample size of 25. So now 25 cars come through. It's still 68% of them are going to be between 63 and 71. So 25 times 0.68. Now, if you've got a decimal here, you obviously can't have a decimal vehicle, so you'd have to round. You'd have to use your rules of rounding. Yes? This didn't come out as a decimal. This was not related to the one before it. You had to redo. It wasn't giving you another 25. Yeah, I think that's what some other kids asked me yesterday. In the sample of additional, these are an additional 25. So just for this 25. Yeah. If you gave it to me based on 100, then you got 68, right? Which is fine, because 68% of 100 is 68. Now, here's the key with rounding to this. Here's my plus or minus 2, 63 to 71. When you round this, say for instance it came out to be 17.5, you want to round to stay inside here, basically. But that's a little bit hard to say, should I round higher, should I round lower? So my advice is you should round lower right now. Stay on the lower, because I know this one works out perfectly, but say it was 71.6. 17.6. Say the answer was 17.6. If you rounded to 17.7, you just win a little bit of a percentage more. You're more than 68% when you round that. So you want to stay within that. You want to round down. You didn't complete another vehicle. This is another one where you're going to round down all the time. Does it make sense, the rounding part? You can't go higher because you're looking for 68%. Higher would be a little more than 68%. So you're going to round down on this side and keep it within that percentage. These didn't have rounding problems, but you might come across one or two where you have to round. Round down on those to keep it within that. Now this seemed to be a little bit of an issue, Chebyshev. Chebyshev's theorem says, pretend that I'm looking at any normal curve right now to see how far away from my mean is my data, and how many standard deviations away from my mean, and then apply my theorem, because this is not really a normal curve. It is skewed some way. Chebyshev's theorem does not take into account the amount that each time is skewed, because you can have a curve that is skewed really, really, really strong like this. You can have a curve that is skewed a little bit like this. They differ. The area under the curve is still 100%. So he came up with one formula that estimates what percentage will fall between those specific standard deviations. You can only do 2 and 3 standard deviations, because he uses this rule right here. One will come out to 0%. It's too fine for him, because he can't decide where the skew is, how steep it is, how gentle it is. They don't really know. So you're going to start as if you were on a normal curve. You're going to put your pieces out there. And then you're going to look at the information he gives you from 0 to 4. How many standard deviations away from the mean are you? 2. This is the information you need now to apply to his theorem. You need to know, God bless you, how many standard deviations away from the mean you are. So now, normally, this would say 95% of your data lies here. But it's not, because it's not an even, normal, symmetrical curve. So you use his formula, you plug in the 2, and you can be guaranteed that 75% of your data on this non-normal curve that we don't know what it looks like will fall between 0 and 4 pets. See, it's a big difference from 95, isn't it? But he's guaranteeing you 75% of it should be there. So out of your 40 households that you sampled, 75% of those have between 0 and 4. You had a lot to do with this one problem. And you take 75% of your 40, and you come up with 30 households. 30 households out of the sample that you sampled, your 40 that you sampled, 30 of them should have between 0 and 4 pets. And that's a variety in itself between 0 and 4. Okay? If we went one further, we can't really give a negative, but we can say this is 0 to 5. 0 to 5 would be at a 3, This is about almost 89%. And it looks like it probably would be 99.7, almost 100%, but he's just a little bit under that because there's some kind of an unknown skewness here. Okay. This one asked it a little bit differently, but notice each time it says apply his theorem. The mean score is 88 with the standard deviation. Now he's telling us, I want you to be 2 standard deviations away from the mean. So you have to map out your 2. Whether you do it like this, take the mean, plus or minus 2 standard deviations, or you set up a graph, either way. 88 plus or minus 4 times 2. So this is going to give us 88 plus 8, 88 minus 8. These are your 2 numbers. You can do it this way, or you can do it off your graph, whichever way you find easier. 75% of your data is going to fall between these 2 scores. He just asked the reverse way. So you interpret this as between 80 and 86 on your test exam. 75% of the kids that took this will score between 80 and 96. And this is a typical one like I told you yesterday. My test scores don't follow a normal curve. More of my grades are higher than they are lower. It should be. It's a college course. So same thing with this exam. From 80 to 96, more of your grades are there. They don't follow a normal curve. You know, if you're 100 here, you're not 0 on that side, is what I'm saying. It's not a normal curve. It's a skewed curve. Questions at all? No? This one, you kind of had to make, they told you to make a frequency distribution out of this. They gave you the numbers on the top because it would be a little hard to find. So they gave you the numbers. All you had to do was make me an L1, L2, put it in your L1, L2, do a 1-pair stat, L1, comma, L2, or in the yellow calculators, the frequency is your L2. You can't be backwards on that. What happens is, even though it multiplies this, and it doesn't matter which order you multiply, it adds the L2 up to be your total frequency. So if you switch them around and make your L1 and your L2 reverse, it will end up adding this column down to be your frequency, and you don't want to do that. So order matters in this. So make sure you do a 1-pair stat, L1, comma, L2. Good? Okay? And they took a pie chart, which this was a little different. There's no percent on the pie chart. They said they put their frequency in their pie chart. It showed the number of students per week that studied. So this actually is a frequency in their pie chart. And since it's 0 to 4, we can't put 0 to 4 in your L1, we use a midpoint. So if you take a look at from here to here, your class width in here is 5. So if you found your first midpoint, add 5 all the way down. And they used, this is new for this book this year, a 30 plus hours. They gave us a midpoint to use. They actually used the same formula that we used, but I haven't seen that done in the past. So we used the midpoint that they gave to us, and again, L1, L2, and you'll get your mean and your sample standard deviation versus population. They took a sample of college students. Even though this is a complete circle graph, it's not the population of all the college students, it's a sample of them. Everybody's good with these? Good? You're not bad. The calculator is the best, yeah. That's why I like to go through one so that you know where standard deviation comes from, but really, why should you do that? Why should you suffer the way I had to suffer when I was your age? Okay, to compare 2 different data sets, we need a way to compare how they vary within itself, within its own mean and standard deviation. So we took a look at 2 cities, and we looked at their entry-level salaries for their accountants. Now, you can't compare and put this all in one data set because their means and their standard deviations are both different. The mean and the standard deviations for Dallas versus New York, look at the difference. First of all, New York has a higher mean. Second of all, New York has a larger standard deviation, which means there's a little bit more spread in their variance, doesn't it? And your coefficient of variance should show you that. Can you see it right here too? I mean, it's more variable in there. All this is a ratio. Your ratio of your standard deviation to your mean, whether it's sample or population. It's just a ratio. And we flip it to a percent, if you move your decimal or you multiply it by 100. New York salaries have a little bit more variance than Dallas salaries. That's all I meant. So remember that problem that asked you if your mean was 33,000 and you wanted to ask for 36,000? You have to go to a firm that has a little bit more variance in there. If they're real tight about the mean, there's no way you're going to make a larger salary. If they're more spread out, the larger the standard deviation, the more spread out, you have a better chance of making a higher salary. Make sense? That was it? Oh no, this is the last one. Here's your entry-level electrical engineers for Boston and Chicago. Now Boston has a higher salary mean than Chicago, and it also has a larger standard deviation. So compared to its salary, it's more variable in Boston than it is in Chicago. Can you kind of tell by looking at the standard deviation alone that it's more variable, it's more spread out? The larger the standard deviation, the more spread out your data. Right? Makes sense? No? Well, tell me what you see. When you look at this versus this, you tell me which one, if you were looking for a job as an electrical engineer, where would you be more apt to go? Why?
Standard deviation for sample was bigger, larger.
Larger. And what about their mean, their average salary? It's higher. They're higher to start with, right? So you probably would pick them. However, if I did this, made them higher, but I made their standard deviation a lot smaller, you might not pick them. Because now, think about it. Let's just make it 1 to make it easy. If I do this, and I put their mean here, then it's only going out 75, 76, 77. You're not making that. The chances of you making, remember, if it's bigger than 3 standard deviations, it's very unusual. The chances of you making higher is very unusual. This is the guy that's running the show here. Just like Damani said. If I do this, and I keep this, and this is 66, now you're 70, 74, 78. You're more spread out. If you wanted to ask for 74,000, it's unusual, yeah, but it's not as unusual as if I'm closer to the mean and I'm in the plus or minus 3 area. So it's not only the mean that's intriguing for us too, it's the standard deviation that catches us. How variable do you want this to be? What was on you? Okay, questions on this at all?